Can you 3D print a 4 foot by 8 foot CNC machine? Let's find out. Okay, hi guys, welcome back to the workshop and to this installment of how to build a homemade CNC machine, hopefully for 1500 quid. So in last week's episode, we finished the torsion box table. I gave it a quick paint off camera. And now in today's video, what we're going to be doing is we're going to be building the X, Y and Z axis for the machines. So what we want in order to do that is we need some kind of linear motion system. So I've built a test here and then I'll show you how this all goes together in a minute. But basically what we're trying to achieve is we've got a series of bearings in this 3D printed part, and it's riding on a 40mm steel box section. And you can see because the bearings are mounted inside, we get nice smooth linear motion up and down along this rail. So there'll be a series of these rails, and that is how the machine will actually have its motion in X, Y and Z, and that will allow it to reach any point on the inside of the table within a certain work area. So I'll bring the camera in a bit closer and I'll show you how to put this together. Okay, so here's what we're going to need. We're going to need our 3D printed carriages, which are here. I think you need 8 of them. You need your 608 skateboard bearings. I got 40 of these. You need your M8 washers. These I think they're like 15mm in diameter or something. They have to be less than 20mm in diameter. Nylock nuts, also M8, 25mm M8 bolts and 100mm M8 bolts. So to start with, we're going to take one of these, and 4 of the 25mm bolts, and these slide in here. It's a bit of a tight fit, and there you go. There's the 4 M8 by 25mm bolts fitted into this piece of the carriage. And then you want to crack on and get that done with all 8 of the carriage pieces. Okay, so now on to the next step, which is fitting the bearings. Take a few of your washers and a bearing. Okay, for the next step, we're going to be attaching these 2 pieces together so that they're offset from each other like this. And to do that, we're going to use 100mm M8 bolts. And I'm using flange nuts because they go on a bit quicker, but you can use nylocks for this as well, if you've got the patience. Then onto that, we're going to add 4 more nuts. Okay, so here's a piece of steel box section that I cut off the rail. That needs to go there roughly. Persuade it into place, and we want there to be a nice tight grip on the steel box section without there being any play. So you can see it doesn't have any play in the ends, but it still rides back and forth nice and smoothly. So then we just want to put 4 screws on the top here. that can be taken out now. Okay, so that's how you put together one of the carriages. I'm going to crack on and do the last remaining two, and then we'll be on to the next step, which is installing the rails onto the torsion box table. Okay, so literally there you go, guys. That's taken maybe 20 minutes. We've got all 4 of our linear carriages. They've all been completed. Next up is attaching the rails to the bed. So we'll crack on with that, and I'll be back in a minute. Okay, guys. So the next thing is we need to mount on these rail holders. And so you can see here that the 40mm box section slides into the top, and the bottom has room for either an FK or a FF bearing mount, and the ball screw will go into that mount at the bottom, and these are going to be attached around this location. So to mark out exactly where that needs to go and where the screw holes in the bottom need to be, I know that it needs to be set in 12.5mm from these edges. So I'll use this 12.5mm piece of ply. And then on here, I've just taken an impression from the actual 3D print itself, and that gives me the bolt hole locations. So just line my piece of paper up with those 12.5mm marks that I made a second ago. And I can just transfer through the holes to show where the bolts need to be. So I've got 4 marks there, and that's exactly where the bolt holes need to go in order for the piece to be mounted on. And then I'm going to drill these out to 5mm. It will be a 4mm bolt going through with the washer on the end, and that'll just give me a little bit of wiggle room in case they are slightly misaligned. The rail mount is installed, and the way I did it was I had to come underneath the table. I'd already drilled a big hole in the bottom, so I had to reach up through there, put the bolts through the small holes that I drilled in the top, and basically then I was able to drill that into place and bolt it in with an Allen key. Okay guys, so I've mounted the 2 rail supports down this end. The next step is going to be to mount 2 rail supports at this end. They have to also be mounted at the same time with the rail and the carriage. So I've got most of my bits set up here, and we'll get those fitted, and I'll bring you along. And let's just now fit the other Y-axis. Okay, so now I'm just going to fix some bolts up through here, and that will be both the rails for the Y-axis complete. Okay, so now we need to mount this plate onto the linear carriage, and this is what the X-axis will attach to. So I've got some M8 by 40mm bolts. They're going to go through the holes on this plate and into the linear carriage, and I've inserted some M4 nuts into the spaces in the carriage. Okay, that seems much better. That's taken the play out now. And then we just need to do the same to the other side of the y-axis, and then we'll be ready to mount the x-axis. Okay, and then you need your 2 x-axis rails, your 2 x-axis bearing mounts, and your 2 x-axis carriages. And then we're going to assemble them together and mount them onto the y-axis. Okay, so you can see I've got them roughly where they're going to go. I'm just going to find some little packers to put underneath to lift it up to the right height and then bolt it in place. Okay guys, so I've mounted the other end of the x-axis in place. Like I said, I just propped up the rails on some boxes to get them to the right height, and now I'm just going to put in the nuts and bolts on this side to fix this part into place. So you can see there's some small hexagonal holes here which the nuts push into. Okay, so I've had a look at all the bits and pieces that need to go on for the Z-axis. So we're going to have some linear rails and ball screw and stuff like that. But looking at it, I think the way it needs to go on is this panel needs to go on first, and then the back panel can go on, and then all of the motion system can go onto this panel. So mounting this is exactly the same as mounting these side panels. Okay, so there's the basis of mounting the Z-axis board. Obviously I've got 4 more to put in here and 4 more to put in here, but the nuts have to be held up against gravity, so it's going to be a bit fiddly, so I'll do that off camera. And it's exactly the same process for mounting the Z board onto the back. So check out Sailor Pete's channel. He designed the Root CNC. I bought these plates off of him and he put the riv nuts in for me. And bear in mind, I've never built a CNC machine before, so I'm no expert. But this is well thought out, so that's why it's all going together nice and smoothly. And I think quite a few other people have built this machine as well. So that always helps. There's a useful Facebook group if you have questions. Just check for Root CNC on Facebook. Okay, so let's try the first little bit of powered motion. Yeah, boy. That's sick, I could do that all day. Right, okay guys, so here's the first problem that we're going to run into. Basically, the Route 4 CNC was designed to be 1500 millimeters long, that in that direction, and 1500 millimeters long in this direction. But for the application that I need it to be able to cut out a sheet that's 2440 millimeters long. So I've had to make these rails longer than they were originally intended to be. And what that's resulted in is just under the rail's own weight, it actually sags down by about 1 millimeter here. And as the carriage drives along, so when the carriage is in the middle and all the weight of the carriage is pressing down, it can deflect by about up to 3 millimeters in the center. And we don't want that because I don't know if you'll be able to see this on camera, but I'll just flex this by hand. So you can see that that's got quite a bit of play in it. Now, I knew it would have this play going into it, so I have thought of an idea that should hopefully support that. But what I'm going to do is I'm going to take you over to the whiteboard quickly and kind of show you the thought process that goes into how to solve this kind of problem. So I'll do that now. Right, okay guys, so we've got here, this is the equation for a simply supported beam. So K is the stiffness of the overall stiffness. That's 48. That's just a constant. E is the elasticity. I is the I think it's the cross section, or it's like the moment of inertia or whatever. And then L, that is the length of the beam. So this is our beam here. It's simply supported at both ends, and we're looking at the deflection in the center of the beam. So basically, we're using a steel box section. That's 40 millimeters by 40 millimeters in diameter, and that's what the Route 4 CNC is designed for, and that is what plays into our cross-sectional area, or our moment of inertia. So we can't really change that value unless we went up to a box section that was like 80 millimeters in diameter. Obviously, that would double the value there, which would increase our stiffness. But I don't want to change any of the 3D printed parts because this is a known design and it's known to work at the normal size. And also, obviously, the elasticity, we've got a steel box section here. If it was aluminium, it would actually have a lot, the elasticity would not be as good. So that would result in less stiffness. Obviously, if the beam was carbon fiber, that's a lot stiffer than steel, but it would just be way too expensive. So we can't really change our elasticity. And then also, obviously, the length we can't really change because we know we need to cut out a 4 foot by 8 foot sheet. So basically, we're kind of stuffed when it comes to making the beam itself stiffer. But you can see here as well, an important thing to note is, yeah, you can mess about trying to change the elasticity and the moment of inertia as much as you want. But realistically, like, L is to the 3rd power. So if you make the beam shorter, you're rapidly increasing the stiffness of it. If you made the beam say you made the beam 3 times longer, then it would be 3 to the power of 3. So 3 times 3 is 9, and 9 times 3 is 27. So the beam is going to be 27 times less stiff if you triple the length of it. So basically, yeah, that kind of is why the beam sags, and you can calculate exactly how much the beam will sag under its own weight, or if you apply a load to it. But we need to kind of look at the problem in a different way. So yes, the beam is that long, but what if when the carriage moves to the center, what if there was a support element here? Then basically the carriage is acting as its own support, and the unsupported length of the beam then is only 1,500 millimeters. And if it drives anywhere along this region here, the beam would actually be supporting, the beam would be supported by the carriage. So that's kind of the problem that I'm looking to solve, and that's the approach I'm looking at using to solve it. So I'm basically going to mock up a little prototype on the actual table itself. I'm going to see if that looks like it's helping with the situation, and if it is, then I'll 3D print out some parts, and I'll just kind of tidy it up and make the prototype a bit nicer. So yeah, I'm going to try doing that now. Okay, and just to illustrate that equation with like a real world example, so here I've got the ball screws. This ball screw is 1500, just over 1500 millimeters long, and you can see that it is quite rigid and it is quite stiff. There is some flexibility to it, but if you compare it to this ball screw, which is 2.5 meters long, this is like a piece of spaghetti. Like, you can see how much deflection that has. So we will be running into a similar problem with the ball screws, but I've got a solution that I'm thinking we'll be able to fix that. When it comes to ball screws flexing, that's called ball screw whip. So we're going to need to eliminate ball screw whip. Again, it's the same principles. One way to do it would be just to make the thickness of the ball screw much thicker, but again, you're going to be adding a lot of cost for that. So we're going to try and come up with some kind of support mechanism for this, so that as the machine moves back and forth, this beam is always supported in the middle. And if that can be achieved, yeah, so if we can support that 2.5 meter ball screw in the center, it should act more like this ball screw here, and it will have less screw whip. Yeah, so I'll crack on with the rail first and we'll show you that. This will probably... Okay, so step one is we need to add some additional rail material. So this is just some 25 millimeter flat bar. I think it's 5 mil thick. I've drawn a pencil line across the table with a spirit level, so that's relatively perpendicular to the table. Okay guys, so what I've done here is I've 3D printed out the moving steady support. You can see that here, just to make it look a bit nicer than a piece of plywood. And what I've done is I've made it now so that the bearings are double supported on each end, and these are eccentric nuts here, and they can be twisted up and down, and that will vary the height of the bearing. And I've got that. Okay, so here I've got the extra long lead screw that's ready to be mounted to the Y-axis. I've got my FK12 bearing block here, which is going to go on this end. Like so. And then there's a retaining nut that goes on. To make sure I put that on the right way around. Okay. And now this is going to slide in through here, in theory. And then this part of the mechanism goes up inside here. Good, so that's ready to be bolted in at that end. And now I have the FF12, which is the free floating bearing block, that goes on this end. And then that can all be bolted into place. So I'll just show you spinning the lead screw at 2000 RPM, and you can see how much screw whip there is. There's not really any. Okay, so this is at about 1000 RPM. And then this is 2000 RPM. There's actually a bit more at 1000 than there is at 2000. And that's obviously with the ball screw nut completely unsupported. So once that's supported, it should be a lot better. So instead, what I've decided to go with is basically there's just a very small shallow box like this with a hole in it. And then inside this, there is a flappy kind of paddle, which also has a hole in it. And then a shaft goes through that for this flappy paddle to rotate around on. So it can rotate in both directions. And then on here, there's a tension spring that goes down and that's just fixed onto a fixed point on the table. So basically this end can pivot out of the way as the y-axis moves over. This end can pivot out of the way, and then as the x-axis travels away, it will just flick back up again, and that will work the same in both directions. And this should eliminate the problem of it basically binding up or anything like that. So I'm going to fit that and see how it works. Okay, so here's the flappy flap mechanism, as I've not really got a better name for it. The spring's mounted inside and everything like that. So the basic idea is, as the y-axis drives past, it will push this flap over, and then it will clear that. And then as the y-axis drives away, this will flick back up, and it will prevent the screw from shaking. So when it's down, you can see the springs, the ball screw kind of vibrates like a string. But when that goes into place, it stops any vibration. And that will prevent the ball screw from whipping around and maybe damaging the ball screw. And that mechanism should be much more reliable than the other one that I was trying. Okay, so I've mounted the back plate. That's just exactly the same as mounting all the other plywood pieces. And then I'm going to mount the Z-axis motor holder, and then the Z-axis motor will mount underneath here like this. And there's some slots for tension in this motor. And again, this is pretty much the same procedure as most of the other axes. Okay, and I believe that this goes this way around. Okay, and then the motor will just mount on there with some M5 nuts and bolts. So that all looks great. And then obviously there'll be a belt and 2 pulleys here which will connect the motor drive to the ball screw on this side. And then that's pretty much the Z-axis done. I'm also going to mount a cable chain holder on here. Okay, so now I'm just mounting the X-axis cable chain and rails. So basically there's this piece that needs to be printed out, which is the X-axis cable brace. 3 of the bolts come out here where the X-axis rails mount, and then this just goes back in again with the 3D printed part in place. I've attached a piece of UPVC here, which was just left over from another project that I was doing. And this could be plywood or metal or whatever you have laying around. It just needs to be relatively rigid for the cable chain to sit on. I've quickly put 1 screw in just to hold it, and I'm going to go do the same down the other end. Okay, now that's in place. It just needs a couple more screws in it. And then essentially a few of these bolts are going to come out. This is going to mount on here, and the cable chain will mount on, but I'll show you that in a second. Okay, and then I've adjusted, I had 2 pieces of cable chain which I've spliced them together, and then I've taken a few links off just to make this part here roughly the right length. And then it's pretty much the same as before. A few M4 nuts go into these spaces. And I just need a couple of short bolts. And they can go through like this. Looks good. So now the cable chain's mounted. It needs to be mounted here as well, but basically what the cable chain will do is, as the X carriage drives back and forth, it will just come along and back like this, and all the wires will rest inside the cable chain, and it will stop them getting tangled on anything, and it will stop them bending at too tight of a radius, which could cause them to snap over time. So now this red piece needs to mount here. And that's pretty much the X-axis cable chain mounted, and then as this drives back and forth, you can see the cable chain moves with it. And that's just going to keep everything nice and tidy and give a good clean installation. Okay guys, so that was how to do the mechanical assembly for the Root 4 3D printed CNC machine. If you want to check out the next part, I'll be doing the electronics and getting the machine moving for the first time. So if you want to build your own 3D printed CNC machine, don't forget to hit the like button. And if you want to see if the ball screws are going to whip around, don't forget to subscribe and hit the bell button to be notified when the next video gets uploaded. And if you've got any comments, criticisms, or you want to tell me what I've done wrong, then please leave a comment down below.